In this video we're going to start looking at how we can take energy sources and turn them into a form of energy that's useful to a consumer. And you can see here we're going to start out first of all with thermal power stations. This idea of a thermal power station, it's not a very specific term. It's more just sort of looking at how we take a primary energy source, a particular way that we take a primary energy source and convert it to a source of basically to electrical energy. So when we're talking primary energy sources in the context of thermal power stations, we're usually talking about fossil fuels, nuclear fuels or biomass, because we're going to convert those primary sources into internal energy. So looking at, as you can see, thermal power, we're talking about thermal energy, and so we're looking for somewhere where the energy source is being converted to internal energy, and ultimately it's about producing electricity, and so that electricity can then be used by consumers, and by electricity what we really mean is electrical energy. Now, regardless of the fuel source, there's a few common steps that will be occurring in these thermal power stations. So whether it's biomass, nuclear fuel or fossil fuels, the process is basically the same. And the reason why it's the same is because once the primary energy source has been converted to an internal energy, then from there it's all sort of basically sort of all doing the same thing, just in slightly different forms. So the first thing is that energy from the primary source is going to heat water. So if it's burning fossil fuels, you're going to then allow the burning of the fossil fuel, so the chemical potential energy is being released as thermal energy, and that will then be converted to internal energy of the water. If it's nuclear fuel, the energy given off by fission reactions will again be used to heat water. If it's a burning of biomass, similar to fossil fuels, the chemical potential energy is converted to thermal energy, which again is converted to internal energy of the water. Now, if we heat water, as we've seen already, we know that water will then be turned to steam, and in these particular applications it's going to occur at high pressure. So the idea here is that you don't actually want the water to bubble, you want it to basically just be vaporized straight away. So it's not like boiling water on a stove. It's because it's pressurized, the steam is sort of just produced from the surface of the water itself. That pressurized steam, so we've converted the internal energy now to a form where the steam is going to move, so kinetic energy. So the pressurized steam is directed at a turbine, and the reason why we're directing it at a turbine is because we want to turn that turbine, so the internal energy is converted to kinetic energy. Now that step is sometimes skipped over, just sort of thinking about internal energy being converted to electrical energy, but we do have this critical stage of kinetic energy being involved as well. So that's the movement of the turbine. And the last step, second last, sorry, the turbine is basically the purpose of the turbine is to cause coils of wire to rotate in a magnetic field. And as we've seen, if we have a coil of wire rotating or moving through a magnetic field, that's going to produce a current. And if a current is produced, that basically means we're converting kinetic energy to electrical energy. Now the last step, so this is electrical energy in the power station, we then need to get that electrical energy out to consumers. And so the last step that we're really interested in here is that the electrical energy is distributed to consumers through the electricity network or through the grid. So that's all of the high voltage power lines through to the power lines along the street that you live on, and then through transformers along the way as well, and ultimately to your toaster or your TV or your computer, whatever it might be, where that electrical energy is going to be used. So through the electrical network or grid, we get that being distributed to users. Now, we should already be aware of the fact that whenever we have any energy change or any energy conversion, we're going to see that some of the energy is going to be lost, and so this is also in distribution of electrical energy. Some energy will always be lost. So usually the forms that we're going to talk about there are internal energy and sound energy. What the exact forms are will vary depending on the scenario, but ultimately we need to be aware of the fact that there are always losses of energy. And when we say losses, basically what we mean is that the energy is no longer in a useful form, and it's lost to the environment. Now, the next stage then is to represent those in a way that's meaningful, and that will be in the form of the Sankey diagram. And so the next bit then is to have a bit more of a look in detail at what a Sankey diagram is, and how they represent these sorts of energy losses. So let's have a new heading here, being Sankey diagrams. I believe you should have covered these before in probably grade 8 or 9, but they are in the IB syllabus, so we need to make sure we have a good understanding of the ins and outs. So basically a Sankey diagram is just a graphical representation of energy flows and energy losses. When we talk about energy flows, we're really talking about the conversion from one to another, or from one form of energy to another, and as a result we'll also see where some of that energy is converted to forms that are no longer useful. Now there are a couple of rules to, not rules so much as conventions, with the way that Sankey diagrams are represented. So sources and losses are represented by arrows, and basically it's then sort of the direction and the size of the arrows that becomes important. So arrows are basically drawn to scale, so arrow widths in particular, so we're not really worried about how long the arrows are, it's more how wide they are. So arrow widths are drawn to scale so that we can see how much of the input energy is converted to various forms of useful output and energy losses. The other thing here as well is that the representations that you'll see in IB is that they're drawn from left to right. So sources on the left and then output forms on the right. And the other thing then, so left to right is sort of the useful forms, but the energy losses, now this will vary slightly depending on the representation, how complicated it is. Energy losses are represented by arrows that either go up or down. The ones that you'll tend to see in the textbook and in past exam questions they tend to be represented pointing down, but just be aware that they could represent them pointing up as well. Now, rather than sort of talk in vague terms, we'll just have a look at an example of a Sankey diagram. And this one is taken from a past exam paper. The question here is not so much important, it's more just having a look at what the Sankey diagram represents. So you can see they're moving from left to right, arrows representing the forms of energy, and you can see they're labelled there fairly clearly. With regards to the arrows being drawn to scale, we can see here that the input energy takes up a total of 10 units. Now what 1 unit represents here, we haven't been told, there's no scale, so all we can say is that there's 10 units, and those 10 units represent 100% of the energy at that stage. And we can then start to break that down into these other components. So you can see the width of the arrow here for the first thermal energy loss in the power station is it's 5 units wide, so that represents a loss of 50% of the energy. Now, energy used in the power station, there's only one width of the arrow there, so that represents a 10% loss. Likewise, energy used in transmission, so getting that power from the power station out to the user. And so in the end, you can see that the width of the arrow for energy that's made it to customers is only 30%. So 100% of the energy input gives you a 30% output. Now, the other thing to identify here, we've got transmission and energy used in the power station. There's other forms that could be there as well, so distribution losses. Depending on the use, you'll also then have energy losses to, say, thermal energy, if you're talking about lights, for example. So while the useful energy output form is light, you might also sort of add that there's some energy lost due to thermal energy. In the end, it might be that, say, energy being produced by a lamp might actually only be, say, 1% of the original energy that was input into that particular system. So you can see fairly clearly here that more often than not, the energy losses represented by these Sankey diagrams is going to be quite significant, and the energy that is ultimately used by consumers is a fairly small percentage of the primary energy source. As we move forward, we'll start to look in more detail at specific types of power stations, so nuclear and fossil fuels and wind and so on. But ultimately, as we identified earlier, we're basically just looking at converting to kinetic energy to an electrical energy. But we'll delve into those in a bit more detail in the coming videos.